Okay, today's lesson is a short lesson called Hooke's Law, and it has to do with springs and the force it takes to push or pull on a spring. So in this picture, I have a bunch of different springs, and you can see that it looks like these springs are all at what we would call their natural length, as in nothing's being pulled on the spring, nor is the spring being pushed on. Okay, this is just the natural length of the spring before any force is applied to the spring, whether that be pushing or pulling on the spring. Okay, so the force it takes to stretch or compress a spring, x units from its natural length, is a constant k multiplied by x, where x is the units from its natural length. So a few things. So I'm going to draw a spring. So let's say this spring, let's say this is the natural length right here. Oh, I want to change, I'm going to get that there. Okay, so this is the natural length. Okay, so then, if there is some sort of force exerted on the string or the spring, I better go back to, so let's say it's pulled on then. Okay, this distance from where its natural length is to where it's now at, that is x. I don't know, let's say I'll put a weight on here. That's a weight. Okay, that's what caused it to stretch. Okay, so that x is the length from the natural length, where the natural length ended. Okay, so the force it takes, we're going to call capital F. That's our force. Equals, it says, a constant k multiplied by x. This k is called the spring constant. Which is like it should be the in force units, or the unit length. The unit length. You all know I really don't have this bad of handwriting. It's just like super delayed on this screen. It misses a lot of what I write. Okay, and then x, we've already talked about this. It's the distance traveled from natural length, whether that's stretched or compressed. Okay. Alrighty, so let's try this. Let's see. Oh, actually, we have one more thing. We need to talk about work. Okay, so work, which is in, I think you would have done this in physics, work is in foot-pounds. Okay, and then this is in this section because it has force in it. Okay, and then a distance as well. So what we are going to do is we are going to sum up all of the work. Because the thing is as you start pulling on, especially one of like a spring like this one here. Okay, it might take different amounts of work to pull on this spring, right? Okay, the further you get it away from the natural distance, the more work it requires. Okay, so what we're going to do is we're going to sum up all the work. This is where the calculus comes in. So work is adding up, which is taking the derivative. Remember, that's kind of like an S, you can think about it as like a sum, and adding up all the work, which would be work is force times distance. So this is a way to add up work from different units away from the natural length. So that would also be so we're going to use actual values like A and B for the limits of integration, like how far away from the natural length, that's what those would be. And then force, we know from the previous slide, that's K times X. So force becomes K times X, and D becomes, that's like your change, dx. Okay, now let's try an example. Okay, it takes a force of 10, this is newtons, to stretch a spring 2 meters beyond its natural length. How much work is done in stretching the spring 4 meters from its natural length? Okay, so we know that force is K times X. And they just told us it takes a force of 10 newtons to stretch a spring 2 meters beyond its natural length. That's the X. So what they haven't given us is K. So this is 2 because it's this 2 meters beyond its natural length. So divided by 2, that means K is equal to 5. Well, we're going to take that and use that to find out how much work is done to go 4 meters from its natural length. So you start off at 0 meters from its natural length, and you're going to go all the way to 4 meters from its natural length. And then just using this formula here, kx dx, k we just found to be 5, x dx. Now I'm just going to take this old school and actually take the antiderivative. That's 5x squared over 2 from 0 to 4. Okay, and that is then 5 times 4 squared. 5 times 4 squared, which is 16, but 16 divided by 2 is 8, so 5 times 8 is 40. And then technically minus 0. So this would be 40 and then Newton meters. Put a dash between there. Okay, I don't have a whole lot of homework for you to do. Just try 2 problems like this. Yeah.